In the following conversation, I speak with Julia Berezutskaya from UMC Utrecht about decoding human speech using neural implants. Julia is one of the world's leading experts working at the forefront of brain-computer interface research. This is a fascinating conversation about implant hardware, the information encoded in brain signals, and the AI models used in deciphering words from thoughts. I'm Shane Farnsworth, and this is the Escape Sapiens podcast, supported by the Andrea von Braun Foundation. If you enjoy these conversations, you can support them directly by liking, subscribing, and sharing. And now, here's Julia Berezutskaya. I hope you enjoy.
Escape Sapiens.
What is a brain-computer interface, and in particular, an intracranial one?
Yes, so that's what we do here. So a brain-computer interface is a technology with which we record brain signals in our participants, and we use them to control a computer. Specifically, I work with BCIs, or brain-computer interfaces, for communication. With these, we can help people who have a severe form of paralysis to communicate. So these people cannot talk or often move. So we record their brain activity through an implant, analyze it, try to detect communication messages in those patterns of activity. And with that, we try to control a computer. We can try to display words that we decode from brain activity on a computer screen. Or we can try other forms of control, for example, by controlling a cursor on a computer screen through brain activity.
And so the implant itself sits on top of the brain. There's no wires that enter the brain at all, from what I can see.
Yeah, so you can see the implant as a two-piece technology. So what's important is to have the electrodes that record the brain activity. Those sit directly on the brain surface. For that, you undergo a surgery. And the leads, or the wires, they do come out of the electrodes and connect to that other piece, which is called the amplifier. That is the piece that does the recording of the data and transmits it to the computer. So that thing, the electrodes, they are underneath the skull and they're directly on the brain, but they're connected to the amplifier that's typically outside of the brain. So it's on top of the skull. And that one transmits the signals recorded.
So it's pretty invasive, right? Because you have to enter through the skull and into the brain, or on top of the brain. Who is getting these done? So who are the candidates who are willing to allow themselves to have this procedure done at this point in time, where it's still a developing technology?
So as you pointed out, it is indeed a pretty invasive procedure. So people undergo a procedure called craniotomy. So that's opening up a skull, drilling quite a big piece around and lifting up the skull to get to the brain. Indeed, it's not easy to find volunteers for this kind of procedure. Usually, we look for people who are in a pretty advanced stage of a disease called ALS. ALS is amyotrophic lateral sclerosis. That's a motor neuron disease. So over time, these people develop first weakness in their muscles and eventually a paralysis that leads to their inability to move or to speak. So pretty late in the disease progression, people basically are left with very few choices how to communicate. Often they can only have their eye movements preserved, eye blinks, and can communicate with an eye tracker. But over time, they can lose even that. So we usually approach people who are in this pretty late stage of the disease, who can only use eye tracking as a communication method, because these people are happy to try something else that could help them gain a better way to communicate. Something beyond just, Morse code kind of blinking, just blinking to yes, no. Specifically, with this type of communication, where they just rely on blinks, what often happens is that they really depend on the person they talk to. And they depend on the types of questions that person can ask. So that's not really how how we used to communicating, and people would like to get some more autonomy and freedom back. And with the BCI, we can try to provide them that.
Can I ask today, so with the technology we have today, how much autonomy can you give people? What can you be completely general in the speech that you can generate, or what's the level that we're currently at, the state of the art?
Yeah, it's pretty hard to say. So there are lots of different efforts in this area. So what we try to focus on is decoding of speech. Of course, what people also try to focus on is decoding of other types of movements from brain activity. Like I said, you can try to learn to control a cursor on screen, and you can try to do that by, say, imitating some movements of your hand, for example. It doesn't have to be speech-based. So you can try, say, imagining moving your hand up, left, right, or down, and with that, you could try to translate it to control of a cursor. What I try to do is to decode actual words from brain activity. And one of the ways to use that is through a command-based interface. Say we can decode 20 words very reliably from the brain activity. And you can use that, again, for navigation. So if you would have an interface that's grid-based, you can have the person control the switch from one tile to another to control that interface with words. Again, something like right, left, up and down, select, things like that. And for that, you don't need a lot of words. So you can end up with just up to 10 words. However, there are people researchers who are also trying to do decoding of naturalistic speech. And that's sort of considered as a holy grail in the field because, this is how we communicate to each other. So they want to really enable that for the patients.
See, this is one thing that I was particularly curious about, because if I look down, so the brain has billions of neurons, right? 86 billion, something like this. I just Wikipedia'd it yesterday. And if I look at the interface that you have here, it's got how many? 4 times 10 or so 40 channels, it looks like.
Yeah, this is a 32 channel one, I think. But you're right, it's a limited number.
So it's a drop down in resolution. So what does that allow you to do? Do you have enough power with that many channels that you could reconstruct, or eventually you have to go to a higher resolution, a larger number of channels, or is the technology here sufficient and it's a software problem at this point?
Right. So it's a great question. And lots of people are working on that in our field. So if I can show you. So like I said, this is an older version of a device that we used in one of our implantees, a person with an implant. So that one actually has just 4 electrodes. And these are larger in diameter than the 32 channel sheet that we have here. So basically, this is even smaller, and what we had set up is that sheet went onto that area of the brain that's called the hand knob of the motor cortex of that person.
Can I stop you for a sec? Why the motor cortex? Because not the speech or the language center of the brain.
Yeah, that's a great question. So most of the BCI endeavors focused on the motor cortex, or sensory motor cortex. And that's because that's the area of the brain that we know the most about. And that's the area of the brain that controls our movement. Hence the name. So basically, there is this very famous notion in neuroscience called a homunculus. So that's a map on this part of the brain called sensory motor cortex that has pictures of different body parts spaced out on that part of cortex. Basically with the idea that different parts of the brain along the motor cortex control different body parts. So you have down here more of a face area. So the neural signals that are generated here control movements of your face, including speech.
Okay.
Yeah, and up here you would have a hand area. So those neurons would control movements of your hands. And the idea here is that people who have paralysis may not be able to control their own body parts anymore, but the brain activity that aims to control, that wants to control, intends to control those body parts can still be sampled by us through these electrodes, and we can still identify the intention to move our body parts or to move our mouths to speak and convert that into signals on the computer.
I see. So the target, it's not that you're looking at someone's thoughts, the word forming somewhere in their brain. You're decoding their attempt, or the target is their attempt to move their muscles that generate speech.
That's exactly right. Yes.
I see. So I interrupted you. You were talking about the resolution.
Yes, that's true. Basically that also kind of explains why we were focusing on this area specifically. And I guess what I was going to say is that in our previous person who was implanted with this device, just with 4 channels on the hand area, we were able to reliably decode one event, and that was attempted hand movement. So every time the person would try to move her hand, we would be able to pick up on that and generate a mouse click on a computer. So this enabled us to create a system with which we had a scanning frame going through different tiles of a grid on the computer. And whenever she wanted to make a selection, she would try to attempt a hand movement, and then the selection would be made. So she could navigate through different menus of the computer, and she could spell. She would have a speller, again, with the scanning frame going through the different letters and selecting the letters that she would want to spell out. So that was possible with just this pretty, coarse resolution of just 4 channels. To be very honest with you, this was possible with just 2 channels out of 4. So the differential signal was computed between just these 2 electrodes. And
so you were measuring a voltage between the 2?
Yes.
I see.
And through that, you could enable this control. You could see the intention to move or the attempted movement very clearly in those signals.
So then can I ask, what is the what does it look like, the signal? Is it temporal or is it spatial? It sounds like it is a little bit spatial because you have this voltage difference between the 2 electrodes that are separated from one another. What does the actual signal look like, and how messy is it? It's
pretty messy, yeah. These are typical biological signals, so it's pretty complex type of signal to work with, non-stationary and everything. So indeed, there are both temporal and spatial dimensions to the data. So when we talk about the spatial dimension, then each of these electrodes, depending on your setup, if you record bipolar, then you get differential signals. But if you can also have a reference somewhere else and then record basically a differential signal between each of these electrodes with one external reference, then you get, say 32 signals for each of the 32 electrodes. So that's the spatial part of it. And of course, the signals also change in time. And the resolution in time is really high, typically 2000 hertz. It can go beyond that. And this is the raw data that we collect. And then through pre-processing, we can try to make more sense out of it.
Have you ever been there in the room as someone who's otherwise locked in, has been able to communicate with their family again, maybe for the first time? Or have you had this experience at all?
I've seen movies. So it's quite a sensitive and difficult thing to accomplish, to go to those people and work with them and make the technology work. So we try to minimize the number of people who do that. We have dedicated personnel who does so-called home visits. So these are trained people who know how to interact with we call them users, and they know how the system works. So we as data scientists try to, take a step back and allow them the privacy and the comfort of working with the system without too many people watching.
So in that case, can I focus again on how you're collecting the signal? So how exact do you need to be with the intracranial implant? Do you need to be very precise with where you put it, or is the system robust enough that you can get the general area and that's fine?
Well, it's quite an elaborate process actually to to figure out where to put the implant. So it's very important, I would say, or at least our experience so far has been that it is quite important to plan this out as much as possible. So prior to an actual implant taking place, what we do is a mapping, pre-surgical mapping. This typically involves an fMRI scan. So a person goes into an MRI scanner and they perform different tasks that involve attempted movement of hands or attempted speech. And with that technique, with fMRI, we are able to get the full brain covered, of course, and we can get an idea of where the activation is for that specific person. Because, yes, we know that the motor cortex is there in everybody. There is still quite a bit of individual variability in the specific parts of the motor cortex that control different body parts. So for that specific person, we do that pre-surgical fMRI scan to understand where the activity is. And then we use those maps where we see the activity across the motor cortex for different tasks, speech movement or hand movement. And we can pinpoint the very specific locations down to the millimeter where we want these implants to go.
Can I just stop you for a sec? So by fMRI, you mean functional.
Yes,
so
functional
you're speaking to the person and you can see the activity in their brain lighting up in the different locations, but it's magnetic resonance. How does this work?
Yeah, so this is a technique that's used very often in neuroscientific research. People just go in a scanner and they perform a task. So it's quite structured usually. So it's not like, we can casually converse with a person or try to converse with them and then we get a brain lighting up with activity. Usually it's something very specific and boring. They just see a task on a screen and then they're asked to attempt to say a word, like an apple or something. And then they're asked to do that 20 times in a row. And we compare the activity that we collect during that time to rest activity. So it's kind of a baseline that we subtract away from the activity during the apple pronunciation. And then we can see what is left over. And that would be the activity map that is specific to trying to speak the word apple.
And are you reconstructing individual sounds or the word apple itself?
Well, we are not really reconstructing the sounds or the word apple. We're just trying to get an idea of what parts of the brain, what activity in the brain is involved in saying the word apple or trying to say the word apple. So the people just trying to make a cognitive effort of doing something. And then we just look at the brain scans that are associated with that task. I don't know if I'm explaining things.
Well, this is in the pre-screening prior to getting the implant put in.
Yes, exactly.
So I'm sort of jumping the down a little bit.
Okay.
So in that task, you're just looking at the specific area of where to do the implant, and then later on, when you actually have the implant in place. Sorry, I was jumping, going ahead of the story, but so then when you eventually do have the implant, at that point, is the target the individual sounds that make up a word, or is it the word apple?
Yeah, so there are different strategies that you can follow. So you can just try to decode, we call them discrete classes. So basically just a number of different items. You can try to disentangle those different items in the brain activity. And that could be having a person to say apple, banana, orange. And you trying to see, can I make a discrimination between these three different things in the brain activity? If you can, then that's great, because you can then pair these with three different things. So whenever the person is trying to say apple, you can control a computer in a certain way that's different from a banana. So that's why earlier I was talking about up, down, right, and left. So these are the few classes that you can try to discriminate in the brain activity and control a computer with that. However, when it comes to speech, what you could also do, like you mentioned, is trying to reconstruct the actual speech. And that could go beyond these discrete classes only. That could actually allow you to reconstruct continuous speech. And that's something that we've been trying to do as well. It's quite more challenging though, because just as a task, it's much harder to do. You need a lot more data, and you need more powerful models to do that. And you might need a higher resolution.
And how generalizable? So if you go ahead and you do this work on one person, you set them up so that you can at least discriminate, let's say 20 words, something like this, not continuous speech, just discrimination of some words. And then you take the software that you've developed, someone else has an intracranial implant, and you use that same software. Does that work immediately, or how similar are the brain signals from one individual to the other? And also for a given individual across time. So once you've set up the device, a week later, does it still work?
So there's quite a lot of variability. And it's complicated by the fact that these implants, of course, are quite rare. So like I said, the person that we had an implant with a few years back, 2016, had this 4-channel implant, which is going to be very different from this 32-channel implant. Or actually, now we're in the process of involving a participant for an implantation of 128 channels. So this scale up makes it hard to directly port the models that we had earlier to this suddenly much higher dimensionality of data. So we may have to change a few things to see how it works now. So in principle, we want to reuse as much as possible. Like if we had a model that worked previously, we want to see how well it will do now with a new participant. But in reality, usually that requires quite a lot of adjustments for many reasons. Intersubject variability, but also this just technological changes. And regarding the variability over time, there's also quite a significant amount of change over time in one person. That is also due to lots of things. It could be due to the technique you're using. So what we have here are so-called electrocorticography electrodes. So these go on top of the brain. In general, these exhibit less variability in signals that they record over time. But another technique that's also very popular in the field is called microelectrode arrays. So these are needles that get kind of inserted into the brain tissue. And because it's in a way more invasive, because they're kind of inserted in, over time the signal changes there quite a lot.
I see.
So you need a different type of models to account for that variability over time.
With those implants specifically, where you have wires that are entering the brain, how do you do that without damaging the brain? Because I imagine the brain actually moves around, and then you have this device which is connected to the skull, is it, in place? And so the brain must move in relation to the implant to a certain extent.
I'm out of my depth on this, but I know that our neurosurgeons fix the implant so that it doesn't move around. They must do some additional things, stitching and something that makes it stay in place. But that's something we also keep track of, that over time the implant doesn't move, that it stays where it was put originally.
And are you seeing... Is there damage to the brain as a result of the implant? Now, these ones that you're using, what's the story there? Is it relatively safe once it's implanted, or how does that look?
Yeah, so with the implants that we're using, the ones that go just on top of the brain, the risks are mainly related to infection during the surgery. There have been many studies done with these electrodes in animals, so preclinical studies that show that over time these implants can stay for years in the person or the animal, and they do not cause any additional risks for the individual they implanted in, and that there is no damage to the underlying tissue. It's a different story for microelectrode arrays that get really inserted in. These are, as far as I know, actually restricted in for how long in the duration of time you can use them for. I think over 5 years, a few years, they have to be taken out. if I'm not mistaken.
And that's because they cause scarring, or what's the limitation
They
there?
cause scarring, yeah.
Okay.
Indeed.
I see. And so the patients that would be having these already, you have patients that need these arrays for other reasons, right? And so they have epilepsy, or there's some other reason why they have an implant, and then you can do studies on these cases.
The electrocorticography electrodes, yes. This is also a way to study medication-resistant epilepsy, indeed. But these are implanted then temporarily. So a person has them implanted for about a week. Then during that time, they're continuously monitored, and the clinicians can get an idea where the sources of epilepsy could be. And then after a week, they're taken out.
Okay, so it's probing where a problem is in the brain by placing electrodes all the way through the brain.
Sort of, in a way. Usually they have some sort of an idea that where they could be coming from, like it could be a temporal generated epilepsy. So they place a grid of electrodes over the temporal cortex.
I see. And so I imagine there are many, many more people having this sort of an implant. And so is this where a lot of your data comes from?
That's indeed true. Yes. This is basically our sandbox, scientific sandbox, where we develop our models, where we try to understand how these signals work, how to make sense out of them. And this is where most of our research comes from. And having that knowledge allows us to prepare as much as possible for an actual implant and make that work.
If you're targeting it's the motor cortex, you say. If you're targeting the motor cortex, why don't you target instead the nerve that goes directly to, say, the voice box or something like this? Sort of more along the lines of a cochlear implant, where it's external to the brain. Right? We don't have a cochlear implant which is implanted into the brain, right? So why are we targeting the brain as opposed to the nerve that connects to the particular thing, the muscle you're targeting?
Yeah, I think that would be more difficult in a way. Also, I think that surgery would be a lot more invasive somehow, I feel like, because then you would have to go not in the neocortex, but in the older structures of the brain. And I think that might mess more with more of an automatic functions of your body. And I have a feeling that may be a much riskier surgery. So I would say that would be a reason. However, that would be also somewhat out of my depth.
I was imagining that it was going to be for reasons of generalizability, right? Because from what I understand, you deal with people who are locked in, they have ALS, are their nerves dying in that case? They stop functioning entirely?
So that's true. Yeah, they suffer from denervation. That's the process of the deterioration of the nerves in the muscles.
So I was imagining that you'd have situations where the nerve is just not active anymore, and so the brain is really the source of the signal is all you have really left.
Yeah, that is true to an extent. We don't really know what's happening in there. That's a big problem with ALS. There are also so many different specific cases for ALS. There are different groups of ALS, either with an onset called bulbar onset. So that's onset somewhere in the face. And that makes the face be affected first. You can also have a spinal onset ALS. So the face would be relatively preserved, and you first start having the weakness and paralysis in your limbs. So there are different cases indeed. And in the case of the spinal ALS, you will probably have less problem with the nerves on the face. However, what I think we also notice is that over time, in the very, very late stages of ALS, because it's a neuromotor disease, a motor neuron disease, you also start seeing the effects of the disease on the cortex. So ultimately, it takes over all parts involved in the motor control.
So even at the very end,
yeah,
right? And then they die from that at the end when their brain stops functioning, or what's the cause of? This is not the happiest.
This is not the happiest, and so I would say that a lot of that has to do with the decision to go on a ventilation or not. so mechanical ventilation, automatic ventilation. A lot of people don't want to do that, and over time, just the quality of life might decrease quite a lot, and it is not uncommon, at least in the Netherlands, for these people to request euthanasia.
I mean, it must be horrible. You're completely trapped. You can't move. Breathing must hurt. Do they still feel pain, or does that also?
It's hard to say for me. I would imagine to an extent they will. But again, it would depend on each individual case, I think.
So if I ask, so a lot of your data came originally from, it was epilepsy patients that then have this intracranial, what's it called, the type of implant where the wires, and there's two different types.
So one of them is this one is electrocorticography. This has flat electrodes that go on top of the brain, and the other one is microelectrode arrays. Those are needles basically. So you have an array with needles sticking out, and then you just put that array, you can insert it kind of in the brain, so the needles pierce the top layer of the brain tissue. This is
the Neuralink. People would know this from the Neuralink, right?
I guess so. Yeah, to an extent.
So in that case, when you're collecting data in this direction, is there a difference in the brain when comparing someone listening to sound, someone producing sound of themselves, or someone just thinking? If I'm thinking a word, I'm hearing a word, or I'm saying a word, how does that look different inside someone's brain?
Yeah, that's $1 million question. A lot of people have been looking into that in neuroscience and also in the BCI field. We know that in the brain there is another region called the auditory cortex, and that would be situated more in the temporal lobe. So it's a different area that's been defined also quite a while ago, and it's well researched. So when you perceive speech, basically the auditory area would light up. It's also been shown that at the same time as the auditory cortex, there may be involvement of the motor cortex in perceiving the speech as well. And that is related to the idea of you kind of either replaying what the other person is saying or kind of trying to predict what they are going to say. So there is this intrinsic connection between the motor cortex and how you say things and the auditory cortex, how you perceive things. So there's a lot we don't understand exactly how this relationship goes. But at least as the main areas that are involved in the process, there would be a distinction between the auditory and the motor cortex. And regarding the sort of imagined speech, I guess, something that you also mentioned, I think there is really no consensus on how this works in the brain. And I think this has to do with different strategies people employ when they imagine saying something. It also can depend on your personality and the kind of person you are, because I think some people who are very vivid, imaginative people, they can really engage their motor cortex to a larger extent when they try to imitate or imagine themselves speaking. And some other people could think about it more abstractly and not really get to the point where they really engage their motor cortex when they imagine saying something. So basically this leads to the discrepancy in the data and in the literature, where some studies show that motor cortex is involved during imagining speech, and other studies show that motor cortex is not involved, and that there are other more high-level language areas that control this process.
So do you think ultimately one day, or maybe you can do it already, could we determine something about the personality of a person or their cognitive abilities from brain scans? Is that information there in the brain scan to take out?
Well, this information will be in the brain activity for sure, because that's all there is to what makes us us, I think. I think this could become ethically dubious if you were to, analyze what people's personality is like based on their brain activity. So I would be cautious about that a little bit. I think there's been some research that looked at the differences in neural patterns between men and women, and I think that can be a bit of a dangerous territory.
So it's something you avoid?
At think, yes, I would.
But nonetheless, does doing this line of work change the way you think about who you are? Do you see yourself in some sense as a biological robot? Has this work changed your perspective on what people are?
I don't think so. I think my perspective on what people are drove me to this line of work. Yes, I think I've always been kind of, how do you say, very down to earth and regarding, maybe down to earth is not the right word, but very, I don't know, thinking that people are more like biological machines rather than, soul stuff or whatever else, that there is something additional, the 23 grams, 21 grams. So yeah, I think it's always been there regardless of me starting to do this work.
It drove you into this work.
I think so.
So then let me ask, how do you do it in practice? So someone has an implant and you receive a signal from that implant, and now you have to convert this into something that's usable, right? Mm-hmm. So what does it look like on the software end, when you're picking up the signal and trying to process this and turn it into something usable?
Yeah, so typically we separate the process into 2 steps. I guess 3 steps. So the first thing that happens is the signal acquisition. So that's when you receive the data from the amplifier, basically from the implant. You get the data onto a computer. That's the first main thing that you need to do. Once you've acquired that signal, you want to go through the steps of pre-processing. That's the second thing that happens. So you need to kind of remove the information that is not relevant and get the signals to the shape that you can work with. After that, you do the decoding itself. Mm-hmm. So whatever the task is, whether to decode apple, banana, orange, or reconstruct continuous speech, you try to do that. And the final step is the getting back to the user. So the interaction, the interface to the user. So the application that they work with, something that you can exert the BCI control on. So it's either a grid with tiles and a frame that moves around, controlled by the BCI signals. Or it could be a speller application. It could be just a prompt where the person is trying to say words and you decode them in real time, and then you show them back to the person. So it's kind of closes the loop onto the whole process.
So the point is you have some target. So it's some output you're trying to measure, and the input is what comes from the brain. And then you use artificial neural networks or something along these lines.
We use different things. Neural networks are among them.
I was interested about this because I wanted to know whether this tells us anything about how the brain functions, or whether this is just a good tool because we're sort of ignorant about what's going on inside the brain, because they're good general processing tools. Is there anything you can say along those lines of why artificial neural networks are good tools for this sort of translation from brain signals into a usable signal?
Yeah, so there are different points of views on that. I know that the computational neuroscience camp prefers to think or finds evidence, let's say, of neural networks being a particularly good tool to understand the brain because of the different properties that they possess. So that's kind of one camp, I guess, of people. A neuroengineering camp of people mostly, I think, focuses on neural networks because they provide better performance. Mm-hmm. So yeah, it depends on what you're interested in. In the BCI field, we mostly want to provide the best performance possible. And if neural networks are the way to do it, then that's what we do. They're really excellent at relating two different signals to each other. So if we have brains and say speech, we can just fit them into the sort of a black box and establish that connection, that mapping. Then great, we'll go with it. We can try to get in and interpret what it is the neural networks are learning, why they are providing the best performance, and what is it that they learn. Typically, it's quite difficult to do, of course, because those architectures have become quite complex. I know some people use like 100 layers neural network. So it can become really hard to really see what it is that they're doing, why they're best. Yeah.
So what do the actual models themselves look like that you're building? So you said that it's not just neural networks, artificial neural networks that you're using. You have other models as well. In practice, what are you building? Can you give me a picture for what maybe just a cartoon, but what does the actual software look like?
Yeah, so there are, again, a few different things. There is software that we use for research, as we call it. So that's stuff that we use for training our models. Usually we had 3 people implanted, and in the upcoming years, we're going to have a few more. But the idea is that we first have a training phase. So first few weeks after the implant, after the person recovers, of course, after the surgery, we go there with so-called screening tasks or localizing tasks. These are the tasks to generate data for training the models. So this is where we just show the pictures of an apple or a word of an apple, and we ask the person to try and say it. And then we just collect a lot of trials and attempts of that. That's the first phase. That's what the training does. And after that, we're going to try to move away from training to the actual use of the BCI. There we will, for example, try to already build the models based on the training data we had. And then we'll show an apple to the person again, have them try to say an apple, and then in the real time try to decode, analyze their brain signal and decode what it is they said, and show them the feedback for what it was. So we can try to see whether we can correctly decode the target word or not. And if we're good at that, then we can move on to uncued testing. So we can leave the choice of what to say up to them. So they can choose whether they want to say apple, orange, or banana. And then we analyze, decode that, and then we show them the feedback. So that becomes closer and closer to the final application where, they do things self-paced. They decide themselves how they want to control the application. So the final step would be the self-paced, where we don't even cue them for anything anymore, that we don't even ask them, now think of apple, banana, or orange, but they just take any time they want. And then at some point they decide to say apple, and then we need to pick up on that. So yeah, this is quite a process.
So it doesn't sound like something that's going to be readily scalable, right? Because do you have any idea for the number of people around the world that might need this sort of technology?
It's very hard to estimate. I would say a few thousands of people.
So if you have to go through this process, I imagine eventually your target will be some sort of a product that really people can use in their own homes, which they can maybe even self-train.
Yes. So yeah, that's why I guess I started saying that this is the research part of it. And the second part of it would be the home use part. This is when a researcher is not necessary anymore, and a person can just use the BCI setup at home independently on their own. So that second part is really hard to achieve because the first part takes a really long time. And with the grant that I previously mentioned, we want to close that gap and to allow the system to be available for people at home so that they could indeed either self-train or in some way just make the home use available as early as possible.
And so far, when in your testing phase, how good have you gotten things? So you said 20 words.
Well, yeah, we aim to do the 20 words now. So at the moment we have 3 implant projects running. There is Corticom, Intense, and Intracom. These are all different consortia. And the goals across all of them basically are to enable this command-based, at least the command-based control of a computer, where we have from 20 to 50 words. We have different strategies there of what words to decode, and how to enable the control of a screen with those commands, depending on the project. But yeah, this is still something that we're hoping to achieve.
So the 3 users, I think you called them, that you've implanted, what have you achieved there along those lines?
So because all those only had the 4 channels, mostly we were focusing on enabling the click for them. And the main I guess advance of that of those projects were the home use. Was the home use that the people could use that system independently at home. So it was not decoding continuous speech or even 20 words. It was just decoding one event, but it was extremely robust and high accuracy. So the accuracy there was 99%, 97, 99%. So people could really control a computer and spell on their own without the researcher supervision. And yeah, we've talked to those people and they were able to do that. And at some point in one of the participants, when her ILS advanced beyond the stage where she could reliably use any other means of communication, like a night tracker, that BCI system was the only way for her to communicate. Which
must be a really nice feeling for you.
We felt very happy that we could provide that for her, yeah.
And so it's 99% accurate, and that's across time as well. So it was something that was stable.
Yes.
Once it was, how long is this person still alive? Or?
She's still alive. She was implanted in 2015. Okay, so wow. She's used the system for 8 years.
And is there an internal? No, the battery is external, or
so the battery was internal and it was replaced at some point. The battery life was, I think, 5 years. So she had to go through one surgery in that time to replace the battery.
That's pretty amazing. So it's already in place, and you already have, to a certain extent, a successful setup that someone has actually benefited from.
Exactly. Yeah, that's why we're very hopeful about the follow-up projects.
And what's the timeline for the follow-up?
So we're currently very busy because we're now recruiting a participant for our next project, the Corticom project. In the next 5 years, we intend to implant, I think, 4 or 5 people, which is quite a speed up compared to the previous score where we had, I think, 8 years and 3 people. Now we're gonna implant a lot more. And we want to go beyond what we've done so far, of course. So go to command-based interfaces.
So if we get back to the software, sorry, I want to, because I know this is also your area. So for the very simple model where you have these 4 implants, these 4 electrodes, what does the model look like there? It mustn't be that complicated, right? Not with the 4 electrodes, or is it still?
No, this one was very basic. Like I said, there was basically one input signal, one-dimensional signal, because so they had different pairs of electrodes, 2 pairs, because of the differential signals recorded. So it was basically just one signal. It was an input to a model, and the model was extremely simple. It was based on threshold detection. So during the training stage, you identify the changes in the amplitude of the signal, and then you just determine a threshold at which you basically binarize the signal that at that threshold, it becomes a click. And if you don't reach that threshold, it stays as no click.
So in that case, you didn't even need a neural network.
No, it was extremely simple, yes.
And so then the next jump up is how many channels?
So the next step is actually quite a big jump. This would be the 128. And there we're going to have to use more advanced models, of course. Something we've been using for a long time now, and that's been returning quite good results, was just a support vector machine. I don't know if you want me to go into the details of what the actual models are.
If you can draw a cartoon, that would be good. So most listeners probably won't know what a support vector machine is. And to be honest, it's also not my area of expertise. So, but if you could draw a cartoon to help people understand, I think maybe I could start off by saying you have some input, which is 128 channels, which pick up voltage in this case. Is voltage between the channels or?
With a reference electrode.
Okay, so you have a reference electrode and then the voltage
over
of
128 channels, yes.
And you'll be receiving some signal, which is some messy, at this point, God knows what for me, but that's the input. And then the output is some target, like the word apple or something like this, and the machine in between is correlating those two sides. In
a way, well, mostly the machine is trying to discriminate between these different classes in the brain signals. So what happens is you collect different moments, so we call them trials, when people try to say each of these words, let's say. So you'll have 3 types of those trials, and each of them will be collected, say, 100 times. So you'll have that many time points, and for each of them, you'll get 128 electrodes over a bit of time, because it takes you some time to attempt to say a word, maybe up to a second or so. So all that amount of data will be fed into our a classifier, a classification model, which will try to associate the differences between each of those different classes with the brain in the brain activity. So, say for one word you have electrode A go up in amplitude, and for another word you have electrode B go up in amplitude. Very simply. So the classification model learns these relationships between the targets and the changes in the brain activity, the differences in the brain activity, and uses it later on for predictions. So that's after you've trained that model, whenever you see new data coming in and you see an increase in electrode A, you know that it is a signature of an apple.
So this is my ignorance, but for a state vector machine, is that like a one-shot model where you just take input and then output, or is this something that runs in a loop continuously, like RNN or something like that? Like, I actually don't know anything about these.
Well, there is a closed form solution, so you don't need to run it iteratively in that sense. Depending on what we want to do, we can try to run iteratively. For example, we can set up something what we call recursive feature elimination. So that's a technique with which we want to build a robust classifier by removing all of the features that do not contribute information to the performance of that classifier. So for example, out of 128 channels, maybe only 5 of them really contribute information, and everything else is noise that actually makes it harder for the classifier. So with this method, we can iteratively train the classifier by dropping different features at each step and seeing what the performance of the classifier is. And we've seen it many times, actually, that often by dropping features, the performance of the classifier increases. So often we end up with just up to 32 channels or so. Important thing about it is that these 32 informative channels could be distributed on the cortex. So you may still need 100 channels because they would be in different parts of the cortex, the 32 ones that are useful.
I see. So it gives you some redundancy.
Exactly, yeah.
And see, this is originally I asked whether the resolution was sort of spatial or temporal, let's say. And so I was imagining that you'd get some sort of Morse code sort of signal on any particular channel, and that would be the way that, but it's not like that. What does the code actually look like that what does this thing, could you give some idea of, because I have zero image of what these signals look like?
Yeah, well, basically, if you look at single neurons, you get something called an action potential. So that is, a response, an excitation of the neuron as a response to an external stimulus. So the neuron, we call it spikes, and it can propagate that input further down. So that is basically what the neural code is. It has the spikes. So in a sense, it is a bit like Morse code. So what we measure, though, is an aggregation of those spikes across a much larger piece of cortex, because we record everything underneath here, which is hundreds of thousands of neurons. So basically, all those individual spikes get accumulated, aggregated across the population underneath the electrode. And that becomes a very different type of signal. So mostly what we focus on is something called high gamma component of a signal. So we do a time frequency transform of the raw signals that we work with. And we see that in a higher band of the frequencies, above, say, 50, 60 hertz, we start seeing signals that approximate the firing rates of the neurons. There've been studies done that show that recorded simultaneously single neuron activity and these types of population-based high gamma signals from electrocorticography electrodes, and they show very nice correlation between the high gamma signals and the single neuron firing rates, or spikes. So we are confident that the signals that we're working with are indeed representative of the neural code, the underlying neural code, even though they work on a larger scale, more on a population level rather than very precise individual neurons.
But I would imagine that a word is going to, it's not like you have an individual neuron that's responsible for a word or something like this, right? It really is collections in any case that are going to be producing the rich behavior that we see from humans.
Yeah, so it's also a highly debated topic in neuroscience. So there is a famous Jennifer Aniston cell or neurons. You can look that up. So basically, there is a famous work that showed that recorded single neurons in a participant, a human participant, and they identified a neuron that always responded to pictures of Jennifer Aniston. Not only pictures, but also just mentioning of Jennifer Aniston, or like anything related, a word Jennifer Aniston. So anything related to Jennifer Aniston was kind of triggering that specific neuron. And that discovery led to a lot of follow-up work, and there were grandmother cells identified and lots of other things. So basically, people have started identifying, relating individual neurons to individual concepts. So there is this realm of work that kind of leads us to believe that it could be that individual neurons really encode very rich concepts, very rich information, such as somebody's identity.
So after this interview, I'm going to have a Julia part of my brain that's being constructed.
Oh my God. Could be for a little while, but the brain is plastic. So after by the time you get ready for the next interview, it's going to be overwritten by somebody else. So yeah, there is this line of work that we have to acknowledge because it's there. At the same time, we work, of course, like I said, at a much larger resolution. So not single neurons, but populations. We don't necessarily see that effect. We don't see that we have one electrode that responds to one word. So at that level, things kind of average out, I guess. So if there was a neuron, it kind of maybe gets drowned in the sea of neurons around it, because we record an average activity over that piece of cortex. So it's hard for us to say, but what we can also see is that we can still identify individual words or discriminate between several words from the signals that we record. So it could be that the brain employs different strategies in parallel. And yeah, depending on the technique you are using, you can tap into one or the other.
This goes back to one of my original questions, which was, why does this technology even work if we have this massive drop down in resolution from billions of neurons to a few channels? Because it obviously wouldn't work if there was an individual neuron that you had to connect to get the word dog or something. It'd be a very messy and expensive research future, I suppose, this area of. But so luckily we really can aggregate and look at more aggregated data, and that still works.
Yes. At the same time, we also see that as we drop down in resolution, so as we drop down from these to these, so we reduce, well, I'm showing the 4-channel strip of electrodes versus 32-channel. So as we reduce the diameter of the electrode and as we put in more electrodes, we do see an increase in performance. So what we also think about quite a lot is what is the optimal resolution at which we want to look at the different words or different attempted movements in the cortex. We don't quite know the answer to that question. So yeah, we just try out things.
And in terms of time resolution, so how quickly can you distinguish words from each other? Does the user have to sit there for 5 seconds before they can get a yes out, or is it quite quick?
So what we see in our research with epilepsy patients, it requires a few minutes.
For one word?
No. For example, if you want to discriminate between 10 words, I would say about 10, 15 minutes of data should be sufficient.
Maybe my question was misunderstood. What I mean, so you're talking about training in this case. No, I mean, so when they're actually using the finished product after they've gone through training, after they've gone through the setup phase, how quickly can they say the word apple or orange or left, right? Is it that it takes a few seconds for that one word to come through, or is it really live that they can?
Right. So what you're talking about is a latency of the system.
Yes.
So what is the delay between the decoding and the feedback? This can be pretty quick these days. Depends on many things, on how well your system works, on the resolution of the that's just allowed by the hardware. But generally, it would be under 1 second.
Okay, so it's really a very usable system.
It's real time. Yes.
And can you sometimes tell? I don't know whether you could do this sort of an experiment, but what I'm interested in is whether this sort of a system can tell us anything about how thoughts form, and whether or not you can tell that someone is thinking something prior to them thinking.
Oof, this is a tricky question. I would say that that's outside of what we're trying to do, because what we focus on a lot mostly is the motor cortex again. And this is the final stage. This is right before you start, you really say things. So all that thought forming process would take place somewhere else in the brain. And there's a distributed network of regions that are involved in thoughts and language processing, including some frontal areas, of course, and some temporal areas. So yeah, I'd say it's a very complex process that involves a lot of areas of the brain, and I don't think I'm able to look into that with what we are doing in the motor cortex.
Okay, so you mentioned that for an individual, after the system has been set up for them, they've gone through this training process with the neural network or whatever system you have in place. You mentioned that for an individual, the setup isn't static in time. Over a given period of time, the signals may change. How do you ensure that the software is robust to those changes? Are you able to do that, or does the patient or user have to continually return to have the system reset?
Well, that depends a little bit on your setup and on your hardware. So in the case of electrocorticography, so again, those flat electrodes on the brain cortex, I kind of hear more and more that these are quite robust over time. So you don't need to recalibrate, as we call it. You don't need to recalibrate the system very often. So you can train a decoder and continue using it without retraining for months, as far as I know. With those needles, with the BCI that uses needles, you may need to do that more often. Again, because it's a more invasive approach. So there may be continuously some processes happening in the tissue that surrounds the needles. So there we see that recalibration is necessary more often, and you can see those plots of performance that drops down over, say, 30 days. If you don't recalibrate, it's basically a linear drop off.
So currently, what is the biggest obstacle that you have? What's the trickiest thing that's standing in your way to producing, for instance, real speech, or first of all, discrimination between, say, 50 words? What is the biggest obstacle you currently face?
I'd say the hardware. So if we were able to, say, get 1,000 of electrodes, super teeny tiny electrodes placed everywhere over the motor cortex, or if we're talking about speech specifically, over the facial part of the motor cortex, covering everything there is there, I think that could allow us to do much better decoding than we currently can.
I see. So that's the main bottleneck. You just don't have enough data to train these systems. You don't have enough patients. You don't have enough people that have these implanted, and for every individual, you don't have enough channels. Just the hardware does not exist really. You cannot collect that many data points. You cannot get that many channels. Mm-hmm. So then the dream would be that maybe you can give me a timeline for how you think this is going to go. So if you could look forward, say 5, 10, 100 years, then long-term horizons, what do you expect in the coming years?
Yeah, making forecasts for the future is probably one of the worst things you can do.
It's perfect. It's recorded.
I'd say, I guess in 10 years' time, we should be able to decode speech rather well, or at least a limited amount of speech. Mm-hmm. And we should be able to offer this technology to people, not only in the research context, but also just put it on the market, let's say, so that anybody could have access to it. In 50 years' time, I guess, we should have the hardware that would allow us to push that further into more realistic, naturalistic speech, so that people could use it for communication the way we are talking right now. So one of the things that we actually see quite a lot in people is that the latency that there is currently in the system. So I said that it's under 1 second, but of course that depends on what it is the control signal is like. If it's under 1 second for every letter that you spell, and it still takes you several seconds to spell out one word. And what we see now in the people with that we work with is that this timing is really crucial. So often they can be part of a conversation with different people, and the communication people have is really instantaneous. So there's very limited window, very short window for your reaction to somebody else's comments, emotional reaction or, verbal reaction. It can be a few seconds, and then the conversation moves on to a different moments, different topic. But in that time, if it takes the person, say, 5 seconds to spell out their reaction, the conversation is already gone. So you can kind of see that they are almost always a bit delayed with everything. And that gap is really important to close for people to feel like they are naturally talking to somebody. Because, if your reactions are always 5-10 seconds delayed, that doesn't feel very natural.
No.
So I imagine the next step would be to really to bridge that gap, to close that gap, make it as small as possible, so that people can really feel like they're part of the real conversation.
And do you know, so far, it sounds like what you're doing is monodirectional. So you're reading signals from the brain. Is there any chance that you could do the reverse with either technology and put a signal into the brain?
This is called stimulation. People do that quite a lot. There's quite a lot of work on BCIs that involve limbs, like hand control. It's really amazing work. It's really great. So what they show is brain controls BCI control of a robotic arm. So with their thoughts, people can direct a robotic arm to, say, grab an object, put it down, manipulate an object. And what they add now to this is a sensorial component. So as the robotic arm grabs the object, they can stimulate the sensory part of the sensory motor cortex to recreate the feeling of touching an object for the person, to give them this sensory feedback. And they show that this leads to a much more naturalistic interaction with objects. It leads to a fast interaction with objects. So closing this sensory motor loop has a really big performance gain, as well as just, a feeling, as long as it provides a feeling of natural interaction with things. So we see that it works really well with the hand and object manipulation. We think that there could be a gain also with speech, although it's much harder because all of that, of course, happens in your mouth. So it would be harder to provide sensory feedback for this. But I imagine that, again, as the electrodes get smaller, as the hardware gets further in development, we can one day be able to also provide this. So I would imagine that would be one of the focus of research for the next 50 years too.
For the interface, which just sits on the surface of the brain, are you able to give feedback with that sort of an interface, or do you need to have needles that stick into the brain?
No, actually, these electrodes, many of these at least, are designed in a way that allows you to stimulate. You can stimulate those electrodes directly.
And so what about images? So I know that people are working on artificial eyes, as we already have the cochlea for the ears, but do you know where that research has gone? Do you know what the state of the art, for instance, is trying to generate an image in the brain? I know this is a little bit outside of your...
Yeah, but that's something we kind of get a glimpse of within the INTENSE consortium. So that's a big Dutch consortium on neurotechnology. And one of the work packages there deals with prosthetic vision. And from what we see, it looks extremely promising as well. What they do is that they also have needle implants in the visual cortex, and they stimulate those needles to evoke something called phosphene vision. So basically, they evoke flashes of light in people's mind. And with that, they can create contours of images for people. There is a study where they could create contours of letters. So a person could try to identify letters as they're presented, and this stimulation is done to the visual cortex. It's pretty exciting research.
So there's feedback in terms of feeling. We have auditory, we have visual stimulation. Smells, have we done any research in that direction? Or?
I'm not aware of any research, but I'm sure somebody must be looking into it. Or I'm sure that will be at some point done as well.
Are you happy to look at speculation?
Sure.
So away from the actual science?
Sure.
So the questions that people must ask you all the time, which must be very annoying, is questions along the lines of how far away from the matrix are we, or how far away from something where we really... Let me ask a question like this. What is realistic in your... what do you expect to be possible in the next 100, 200 years? Are we going to have real high-resolution feedback where you can watch a movie inside your head or something along these lines? Or is this really just science fiction after playing around with these devices now for some years?
Yeah, it's really hard to say. What we focus on the most is the medical field. As our interests lie mostly in restoring or enhancing, improving the natural ability of people to perceive, to speak, to communicate, manipulate objects and such. So we kind of try to stick with our medical technology application field. But of course, inevitably, people will want to look beyond that and see what will be possible. I don't know what Neuralink is going to do. We'll see where it goes. I'm sure there will be some applications. It's very hard for me to imagine what will be there in 100 years. The other day I was talking to my supervisor and we were thinking how it's funny how I think in a few years back, at least in many movies, sci-fi movies, you could see people interacting with some sort of futuristic tablets or computers where everything is sensory. But the reality is that's not that's not what we do currently. And I don't think we will ever do that because counterintuitively, the physical feeling you get from the actual keys on the keyboard is somehow better for the performance and for your feeling than the screen touch based keyboards that are in every movie from, I don't know, the 2000s. It's hard to make prognosis. You think that something is inevitably going to be great because it looks futuristic, but you don't know whether that will actually be there because, it's hard to estimate what the user needs are. It's hard to know what people will want from a technology like that.
And of course, it's invasive, right? So
Yes.
do you see a place for healthy users using this sort of technology? Or?
That's also hard to estimate. The surgery that's currently required to put in an implant like that is pretty invasive, pretty extensive. I don't think people would want to do that. I imagine it might change. I imagine less invasive surgeries will be possible in the future. Maybe different technology for putting in the implant. There is a technology already right now called stentrode. So this is a minimally invasive implant where they put in a very small sheet of electrodes through a vein.
Okay.
So basically they put in electrodes through a vessel.
So in your neck or something, and it goes up in...
So I think they put it in somewhere around your neck. I'm not entirely sure what the details there are, but they don't need a brain surgery for that. So they put it in through a vessel and they deliver it through a catheter or something towards the motor cortex. So those electrodes, they sit on top of the on top of the motor cortex. So there is a big vein here. And somewhere in here, they put in those electrodes called stentrodes.
And the electrode, does it remain within the vein or
Yes.
it's pushed through on the other side?
So it attaches to the wall of the vessel and it stays there.
Wow. Okay.
Yeah. And through that, they can also do a BCI. So this is a technology that's been pitched by Tom Oxley. And it's picking up. And
is there a wire that then travels along the length of the vein and then you have a pickup point at the neck, or how does that work?
They just deliver it there and it stays there and it just records the nearby activity. So whatever cortex is closest to it. So usually it's part of the motor cortex that controls feet or legs, because this is where it ends up. And they just it just stays there and they record from there. And
So okay, I can imagine that being more palatable to people who
exactly. So it's a lot less invasive, doesn't require brain surgery. It's quite limited currently because they can only record from the area that controls legs or feet more. So I don't think speech decoding is currently possible with this, but we don't know where this will go in the future. Maybe they'll develop other ways of getting those electrodes closer to the facial motor area.
And what does how advanced, how far along have we come? So far you're taking a signal from the brain, and I imagine the speech that you will be producing is going to be coming from a speaker. Right, you're not re-innervating the vocal cords or something like this. Is that in future plans? Are you hoping to be able to give people movement in their face again, or anything along these lines, or is this too far out?
Well, That's partly what I'm looking into. So I have a small grant that explores the possibilities of reanimating facial muscles through stimulation. And the idea would be potentially to connect a BCI to a stimulation device and have people, for starters, produce facial expressions, for example. And then maybe in the future, many years later, even some vocalizations and speech sounds.
And I suppose actually maybe to eat as well, because people with ALS, can they chew?
No, so they actually get their food through a tube. So yeah, of course. And there's also research actually on the diaphragm pacing. So for breathing, stimulation technique potentially could also help with that. So there's quite a lot of research going on, and I'm not entirely sure what the outcome there is, if there is one yet. How promising this technique actually is.
So why did you decide to focus on speech? I mean, there are so many interesting areas in the field. So what is it about speech that catches your attention?
Well, I guess the answer is going to be pretty prosaic. Partly due to my background, of course. I have a degree in language studies, in linguistics. So I guess speech has always fascinated me, and I do think that in the realm of communication, that's probably the way you want to go. You want to have people the ability to actually speak to each other, because that's what we do for communication.
So you mentioned, we both mentioned Neuralink. This is, I suppose, the most well-known company in this area for obvious reasons. How is it seen in the field? So do people in the field take Neuralink seriously, or what's the view?
Well, there are many different opinions. I'm sure I wouldn't be able to speak for the whole field. When it comes to our lab, I think we're pretty happy it's happening. We're happy that it raises awareness about this technology and the medical applications, the possibilities for people with paralysis and other conditions. My supervisor called it riding on somebody else's pony, which is pretty funny. So yeah, it's good that it's happening. It would be nice if the researchers got a little bit more credit, because we've been working on it for way longer. But overall, we hope it will something good will come out of it.
So I want to know what success looks like for you. So let's imagine you're now 80 years old, Julia, looking back on your career. What will you be proud of? What will be the happy thing that you've produced?
Wow, that's no pressure. I guess if I could enable naturalistic speech without big latency, so that people could actually talk to each other, even though they're paralyzed, that would be a great achievement. I think I would be very proud of that.
Well, Julia, it's been a pleasure. Thank you for coming on the podcast.
Pleasure is mine. Thanks a lot. It was a great talk.